The Pico 2 and RP2350 launched with Rust support, and that really woke me up to the potential of Rust. I knew about Rust, but hadn't thought of doing anything with it or considered it for embedded systems. Rust has some big potential in this space though. Support for the Pico and Pico 2 is a great help. Let me tell you all about it. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, Pico 2, robotics, IoT and other fun tech. Remember to subscribe and join the community. Over the years, I've touched many programming languages, from the esoteric worlds of Eiffel and ML to the commercial stars of Java, C++ and Python. I'm new to Rust though, and in this video, I begin to put my toe in the water. This might be the beginning of my shift to Rust as my main language. Hang around to the end of the video for my assessment of whether I'm moving to this new language or not. If you like this video and it helps your learning or projects, why not drop me a cash tip using the super thanks button below the video. I'm saving these up to get myself to open source in San Francisco next year, and I'd appreciate your help in getting me there, and I'd hope to see you there too. Please hit the like button on the video and subscribe for more. This video is sponsored by WolfSSL. WolfSSL provide both open source and commercial supported libraries for security that I use all the time in my embedded systems. But did you know also that WolfSSL actually supports Rust, and we can actually use those cipher suites in the Rust language too as a provider, both using software algorithms and hardware acceleration, which is great when you're playing with Rust. So go check out WolfSSL today. So Rust is new to me. Rust is something that I'm only picking up and looking at right now. You know, when I talk about C and C++, well, I've been writing C and C++ since the early 1990s. So, you know, talking about Rust is really different for me. And Rust has been around for a little while. It was first conceived in 2006 by Graydon Horse at Mozilla. And it's a general purpose programming language. I think the nice thing and the things that starts to attract it for me is the fact that it's completely type safe, and it enforces memory safety as well. And those are something that perhaps would accelerate my development on the Pico 2 and these embedded platforms, because that's where you generally make mistakes in how we're using types and how we're using memory and maintaining memory, because you know that's where C and C++ allow us to play dirty tricks and forget about things and cause problems. It's also got immutability, high order functions, algebraic data types, all of that pattern matching, all of the sort of stuff you really want. Actually, the pattern matching is quite nice. That's quite an additional capability. Nice. And it can even be used in an object-oriented way, which is good because obviously a lot of my design processes are object-oriented. That's where my background was, and something I still really find useful. We can of course use Rust in lots of different ways, from traditional applications to WebAssembly and building websites to networking and embedded systems. And it's the embedded systems that of course we're going to talk about today. So the real claim to fame with the RP2350, the Pico 2 and Rust is that Rust was available and released at launch. And this, I think, is the first chip that's actually had support for Rust come out at the same time the chip was actually released. And that's quite fabulous and quite interesting because it shows how far away, Rust has come on that journey. Now, of course, Rust is actually also supported on the RP2040 and on the Pico, therefore. And you can go and write Rust there. It wasn't there at launch. And it sort of slowly appeared there, and perhaps not all of us have noticed. So the song and dance and you know, a bit of shouting that came with the launch of Rust with the Pico 2 on launch actually really made us all sort of focus a little bit more on the fact that Rust was there. To use an embedded hardware and toolchain with Rust, we use a hardware abstraction layer, a HAL, HAL. And when we're looking at using this for the RP2350 or the Pico 2, we have at least two options available. So two that I looked at anyway. So we could use the RP2040 HAL, which seems to be being renamed, I think, to the RP HAL, which is good because it's going to covers both the 2040 and the 2350. Or there's another one called the Ebassy-RP, which also handles the RP2350 and therefore the Pico too. Now, which to choose? Well, I couldn't see a great deal of difference between the two, really. Your code and setup is different, but you know, it's a choice, and we'll look at both of them in this video. And these choices are something that we are, I guess, are used to on the Pico ecosystem. I mean, if we're choosing to work with C and C++, we absolutely have the choice of going with the SDK or going with the Arduino versions of C and C++ and using that on the platform. If we're working on Python, well, there are two options. We could go MicroPython or we could go CircuitPython. So again, choices. And so Rust is no different. We have the choice of going with the RP HAL or the Ebassy-RP. Before I make a decision around the HAL though, the first thing I need to do is actually get the Rust toolchain installed. And that was actually very simple. If you go onto the Rust website, it gives you the instructions to install it for Macs, Linux or Windows. This installed relatively simply on my Mac. Only thing I would say is that instead of actually editing my .z profile to add in the configuration, it seemed to create a .profile instead. So I just had to remember to manually merge those and handle those, but actually pretty simple. And I was then able to actually go and test it out and write my first local Hello World Rust program that I could just run on my Mac. For the Pico 2, we need to add in a couple of additional targets, and we can use this command rustup, which is actually working as the package manager for Rust. So we're going to add two targets, the Thumb V8M, which is the ARM target, and the RISC-V target, both for the RP2350. And then the code I'm going to do, I could have just downloaded other people's repos and run it. But one of the things I've sort of learned is that if you want to actually show that you really know something, you create the project from scratch rather than just merging someone else's or grabbing someone else's project and building it. So in this, I've actually built the project based on other people's example code, the standard example code under MIT license, but I've actually regenerated the projects because that way I found out more about how the toolchain worked and how to use it in my environment, and I definitely recommend that to you guys. So the Ebassy-RP HAL is based at this URL, and you can find it with all the documentation there, and my application to use it is their application to use it that I've rebuilt is the Pico 2 Ebassy Blink in my project. And I built that going through the cargo new Pico 2 Ebassy Blink to actually create a new cargo project and then to build from there. So over in the repo, the example here using the Ebassy version of this sort of Pico 2 support for Rust is here. And you see there's quite a lot of files in this. We need to give a memory model to explain how to use the memory model on the RP2350. We've got the cargo.toml file, which is actually defining how to do the build process and dependencies of Ebassy, which we're downloading from Git there, you see, and how that's all doing to provide those dependencies in there. And we've also got this build.rs file to control the build process and actually bring in that memory.x file into the process. The source code actually for blinking is actually pretty simple. It's down here. A lot of this looks to me like it's boilerplate and would be common in just about every application you run. So there's a lot of setup of the libraries and pulling in the libraries and configuration before we actually get down to truly the main thing, which is here, which is, as you'd expect, about getting hold of pin 25, which is what's the internal LED on a Pico 2, and then going through this loop and doing these weights of between setting the value high and setting the value low, just what like we'd see in C. Now I can build this using the cargo build command with that minus target option, so I tell it that we're building for an RP2350. I should then be able to use the boot cell process to actually copy it straight over using the cargo run command. But I couldn't actually ever get that to work, and I gave up trying. So the way I actually just copied it over was actually to use the Pico tool with load, and to point it to the binary that it just built. I need to give it the type of the binary because it's not put the extension on there, and Pico tool is dumb and expects files to have extensions. We then also need to tell the Pico to reboot before it will actually start running the code. Doing all that, and we can get the Pico 2 blinking. The RP hardware abstraction layer, RP HAL, which used to be called the RP2040 HAL, I think, is available at this URL. And I've built a version of Blink, or their Blink application, from that called the RP2350 Blink, to test this out. Now, before you install and work with this HAL, there are a few additional things you need to add in. So the target, which I think it may actually be the 2040 target actually, but they're recommending installing it. I did. There's a couple of tools, an ELF to UF2 tool that they put on there, and a probe RS tool, which I think should be starting to support the Raspberry Pi debug probe, but that's not a space I've actually managed to get to. Well, yet anyway. So let's have a look at the project for this one. Over in the repo, we've got the RP HAL's version of the Blink code, and that's in this RP2350 Blink project here. This has a number of files up here that we need to actually set up. There's a memory setup for this. The configuration for this actually allowed this to run on both the RISC-V and the ARM model, though I've only actually played with the ARM model. So we've got a RISC-V configuration file here as well. I probably could have removed that, I just haven't. You've got the build configuration file here, which tells it how to actually bring in both that RISC-V config and the memory config, because we've got to tell it how the RP2350's memory is configured. And then we've got the cargo.toml file, which actually controls most of this build process and defines the dependencies, etc. We're bringing in the RP2350 HAL's support from Git in here. I actually have played around and done that locally as well, but you can see all of the package supports in here. The code actually to build it itself, or run the code itself, again, is a lot of this is really boilerplate. It's sort of, bringing in the libraries and setting everything up, which looks pretty similar to, I think, on every application. Things like what is your clock speed and how is that clock speed going to be then used in order to give us delays, because we're going to want delays in order to set that timer blinking. And then down here we've actually got the code, and it's, as you'd expect, we're getting this LED pin 25 on a Pico 2, which is the internal LED, and then we're going through this loop, just setting it high, setting it low, and in between we're just doing some delays. The unwrap stuff on the end of that, I think, is as I understand it, error handling, in order to handle anything that goes wrong and make sure that we get informed about it. There is one other thing to look at in here, is actually to get this all to build and everything to work, you have to have this config.toml file from this .cargo file. And I didn't realize that, and I didn't copy this over, and I spent a good couple, 2 or 3 hours banging my head against the wall wondering why this all compiles fine. I've got a binary here, but what's in that binary is crazy and not viable to run on a Pico 2. So what's going on? And my problem was I hadn't got this. With this file, this defines actually how to do that build process, and it includes all the magic spells for being able to actually load things onto the Pico via Pico tool. Because of that magic config.toml file, I can actually just now type cargo build, and it knows that I'm building it for an RP2350, and it will run off and run all that build process, which takes it a little while, I must admit. But then I can actually put my Pico 2 into boot cell mode and then use the command cargo run, give it the binary bin blinky, and it will actually copy that all over directly to my Pico and make my Pico run. So we can then see the Pico blinking. But all of this is dependent on having that config.toml file, which seems to be really the key with using this particular HAL to get it all to nicely work. So am I leaving Resort C and C++ in the embedded world and moving over to the new build Rust Resort? Well, perhaps not quite yet. I've done quite well. In just a few hours, I've managed to get the toolchain happily running on 2 separate HALs, and seen exactly what I can do as potential. Now, I haven't actually got SWD debug probe working, so I think debugging my code would be challenging at the moment. Also, to convert myself to Rust, I really want to know whether I've actually got access to the sort of libraries that I use every day. I'd want a real-time operating system. I'd want IP protocols for HTTP, MQTT, and those sorts of things. And of course, support for robotics via something like MicroROS. Well, from what I can see and what I've read, I've certainly got the IP protocol stuff, and I might be able to go down that route. So perhaps not on the Pico 2 right now, but the Pico 2W when it comes out imminently, that might actually be really quite exciting and possible. The real-time operating system, well, not really. That everything I've shown you uses what they call no standard approach to the HAL. That means that the standard libraries for Rust, which include things like threading, are not available to you. So that's kind of limiting. And of course, MicroROS doesn't really have a Rust wrapper at this point, as far as I've found anyway. Going back to that real-time operating bit, there is a really good write-up from FreeRTOS Systems on concurrency patterns in embedded Rust and your different options. And they explain why that real-time operating system isn't really quite there for Rust, and it's about memory efficiency of the stack. Rust protects you in terms of understanding the types and preventing misuse of memory, and it does that by having some additional storage on that stack, which means that stack isn't as efficient as it is in C and C++, I think, and therefore you get a great deal more bloating, which is a problem then on an embedded system. I think that's where they're going from my understanding of FreeRTOS Systems blog and my understanding of what's going on in this. That's a shame. I really would like a real-time operating system, but there are other options within Rust for embedded patterns, and have a read of that article. It's a very good write-up of it. So there are a few things I need to resolve before I move to Rust. I can see the potential though. It does feel a little on the experimental side right now, as I had to fiddle versions a little to get things to work. Perhaps not for my next client build, though sometime very soon I think Rust will be there. Definitely keep your eye on this space. If you'd like this video and it helped your learning or projects, why not drop me a cash tip using that super thanks button below the video. Remember, I'm saving these up to get myself to open source in San Francisco next year, and I'd appreciate your help in getting me there, and I hope to see you there too. Thank you very much for watching. If you enjoyed the video, and I really do hope you did, then please hit that like button, and please subscribe to my channel so you don't miss the next video. Bye bye for now.